Welcome to this lecture on the comparative anatomy of vertebrates. Today, we are going to explore a fascinating topic, girdles and limbs. If you have ever wondered how animals transitioned from swimming in the oceans to running, digging, and flying on land, the secret lies entirely in these skeletal structures. We will uncover the mechanical brilliance behind how our bodies anchor our limbs and how evolution has perfectly engineered these biological machines for survival. Let us dive in and discover the structural foundation of vertebrate movement. To begin our journey, imagine trying to attach a heavy, swinging construction crane to a flimsy wooden wall. The wall would collapse almost immediately under the immense stress. To make the crane work safely, you need a massive, deeply anchored concrete foundation to absorb all the twisting and pulling forces. In your body, your arms and legs are exactly like those heavy cranes, constantly moving and striking the ground. The concrete foundations that anchor these active limbs to your main body axis are called girdles. Without these sturdy structures, your limbs would simply rip away from your spine every time you tried to run or jump. Now that we understand why anchors are necessary, let us look at the formal anatomical terms. In comparative anatomy, the girdles and limbs collectively make up what is known as the appendicular skeleton. You can think of the appendicular skeleton as the structural bridge that connects the moving appendages to the axial skeleton, which consists of the skull and the vertebral column. This beautiful mechanical partnership between the stable anchors of the girdles and the dynamic moving parts of the limbs is exactly what allows vertebrates to navigate their environments with incredible efficiency, whether they are walking, swimming, flying, or digging. Moving deeper into the anatomy, let us examine the first of the two anchors, the pectoral girdle. Located in the front shoulder region, the pectoral girdle has a very specific and fascinating design. Unlike a rigid bony attachment, it is typically suspended by a complex sling of muscles. Why is it built this way? When an animal runs or lands from a jump, the front limbs take a massive impact. This muscular sling acts as a biological shock absorber, cushioning the heavy blow of the front limbs hitting the ground and protecting the delicate axial skeleton from shattering under the stress. While the front anchor absorbs shock, the rear anchor has a completely different job. This brings us to the pelvic girdle, located in the rear hip region. In stark contrast to the muscular suspension of the pectoral girdle, the pelvic girdle is firmly and directly fused to the vertebral column. This rigid, bony connection is crucial because the hind limbs are the primary engines of movement for most land vertebrates. By being tightly fused to the spine, the pelvic girdle ensures that every ounce of force generated by the legs is transferred directly into powerful, rigid forward propulsion, driving the animal ahead. Having explored the girdles, let us now focus on the limbs themselves, which are formally known as choridia in tetrapods. These muscular, jointed appendages are divided into three distinct evolutionary segments. First is the stylopodium, which corresponds to the upper arm or the thigh. Next is the zygopodium, which makes up the forearm or the calf. Finally, we have the autopodium, which includes the complex structures of the wrist, ankle, and digits. This three-part segmented design evolved from the simple, stiff, paired fins of ancient aquatic fishes, transforming into the highly complex, multi-jointed levers we see in modern land-dwelling animals today. Now that we know the anatomical parts, we must shift our perspective to understand how they actually work in motion. To truly understand limb function across different vertebrate species, we must look at them not just as static pieces of bone, but as dynamic biological machines operating as physical lever systems. In physics, a lever is simply a rigid bar that pivots around a fixed point to move a load. In the vertebrate body, the bones are the rigid bars, the joints are the pivots or fulcrums, and the contracting muscles provide the input force. This mechanical setup dictates exactly how an animal survives in its environment. This lever concept leads us directly to a mathematical way of measuring limb performance. The overall performance of a limb can be quantified using the formula for mechanical advantage, or MA. Conceptually, this formula compares where the muscle pulls to where the limb pushes against the world. MA equals L in divided by L out. MA is a unitless ratio, indicating how effectively a limb multiplies muscle force. L in is the in-lever length, the perpendicular distance from the joint pivot to the exact point where the muscle attaches. L out is the out-lever length, the distance from that same pivot to where the limb applies force to the ground. When L in increases, the limb becomes much stronger, but slower. When L out increases, the limb becomes weaker but moves incredibly fast. Before we calculate anything, let us visualize this formula with a clear diagram. Here, you are looking at a schematic of a vertebrate limb functioning as a lever. Notice the elbow joint, which is labeled as the fulcrum, or the pivot point. Just behind the fulcrum, you see a red arrow representing the muscle force pulling upward. The short distance between the fulcrum and this red arrow is our in lever, L in. Now, look all the way to the right at the digits. The blue arrow represents the output force applied to the ground. The long distance from the fulcrum to this blue arrow is the out lever, L out. By comparing these two lengths, we can instantly tell if this limb is built for crushing power or for blinding speed. Now that we have our formula and visual intuition, let us apply this to a real-world example. Imagine we are examining the forelimb of a mole, a specialized mammal that needs massive force to push through heavy dirt. We are given that the distance from the elbow to the triceps attachment, our in lever, is 2.0 centimeters. The distance from the elbow to the digging claws, our out lever, is 4.0 centimeters. We need to find the mechanical advantage. We choose our MA formula because it perfectly models biological levers. We substitute 2.0 for the numerator and 4.0 for the denominator. The centimeter units cancel out, leaving us with a final answer of 0.5. Physically, this is an exceptionally high value, proving the mole's limb is evolutionarily optimized for raw digging power. Let us contrast the digging mole with an animal built for explosive speed, like a cheetah running across the savannah. Here, we are given the hind limb measurements. The distance from the ankle joint to the calf muscle attachment is our in lever, measuring 3.0 centimeters. The distance from the ankle to the bottom of the foot, striking the ground, is our out lever, measuring a very long 15.0 centimeters. Again, we use the MA formula to reveal its functional design. We substitute 3.0 for the in lever and 15.0 for the out lever. Dividing these gives a final answer of 0.2. This is a very low mechanical advantage. Physically, this means the limb sacrifices brute strength, but guarantees that the foot moves incredibly fast for every small muscle contraction, enabling explosive running speeds. These two examples perfectly illustrate a fundamental rule of comparative anatomy. The specific shapes, sizes, and angles of bones dictate exactly how an animal survives, hunts, and escapes predators. A high mechanical advantage, like we saw in the mole, yields raw power, which is the perfect evolutionary design for digging or swimming. Conversely, a low mechanical advantage, like in the cheetah, yields high velocity, which is the ideal anatomical design for running and jumping. By simply altering the lengths of the bones that make up the inlevers and outlevers over millions of years, evolution has sculpted limbs perfectly suited for any physical environment. We have covered a lot of ground today, so let us summarize the most important ideas. First, remember that girdles are the essential, stabilized anchors that safely transfer forces from the limbs to the axial skeleton. Second, the limbs themselves are not just bones. They are highly adaptable biological levers that interact with the physical environment. Finally, the concept of mechanical advantage mathematically proves how altering lever lengths changes a limb's function from generating power to generating speed. You now understand the deep relationship between anatomical form and biomechanical function, which is the absolute core of mastering comparative vertebrate anatomy. Great job today!